Well, thanks to all of you for coming. Really delighted to be here among my two top mentors, so Tom and Peter. So, I was PhD student with Tom, and then later Peter founded the quant research group at Bloomberg, where I still work. But I guess we're missing Bruno Dupier, and that will complete the picture. But so with that, and I see some old colleagues here as well. So it's very nice to see familiar faces. I do have what I acquired, like a little glacier or ice fall cuff. I just came back from a trek in the Mount Everest region, so please excuse me if I'm maybe not loud enough or if I'm coughing in between. It's, it's not contagious. All right. So with that, so the talk is about using machine learning in finance. It's in particular for mining sentiment from news stories. And this is a quote from Alan Greenspan that really sets it up very nicely, where he's basically saying that mathematical models are not as important as just capturing sentiment of investors. So if he had a way to capture the variety of sentiment from the investors, we would be in better shape to model the economy. So this was about a 10-year-old code, but this is sort of setting up this field. And before I go into the topic for today, I just wanted to give a little bit of taste of the projects that we are doing in Bloomberg. So over the last few years, as you all know, machine learning and deep learning has making an impact in all industries, and it's not a surprise in finance as well. So we most of us come from traditional quant finance and computing background, but now we're doing a lot of machine learning. Not all these projects are is something not Bloomberg is working on many of these projects. So for example, we have a Bloomberg Maps product where they map movement of of large ships which are carrying oil and other commodities. So it's important for the map project to also try to mine information from other alternative data. So for example, they're using neural networks to help find count number of cars in a parking lot in the same product. So that's this sort of on the fringes, but within the structured finance world, we are using machine learning to not just mine for sentiment, but also build predictive models. So one of the models that we have mentioned here is number 5, the autoencoder, which is a type of neural network. So we're using neural networks now to help build parsimonious low-dimensional encapsulation of objects like wall surface or yield curve time series. So you may be familiar with techniques like PCA, for example, which are sort of a way to capture a low-dimensional reduction of high-dimensional time series data. But autoencoders is sort of a nonlinear PCA, if you will, which allows you to build very powerful encapsulation of these data for modeling purposes. These are some of the projects that we have touched upon. I will not go into the detail. Variety of tasks from calibration to prediction to anomaly detection is always a big theme. Essentially, advanced statistics and machine learning is really touching upon many of these fields in quant finance in a big way. So with that, natural language processing is also like sort of like a subfield of machine learning, and it's very, very important for Bloomberg, being a big news organization, that we should be able to process news in a very quick time. So we can't afford to read the news in a manual fashion. We need automated, machine-driven news summarization, extraction of topics, extraction of sentiment. And for example, if this is just an illustration of an event such as SEC announcement. So it's important for Bloomberg to get the first headline as soon as an event occurs. and we can't, within 20 minutes of the event, in this case, there was a big drop of 12%. The New York Times story broke out, I think, about maybe a minute or a couple of minutes after Bloomberg. And this is sort of the type of things Bloomberg is actively sort of trying to be ahead of the curve for generation of machine-driven content. And in the same business in Bloomberg, sentiment analytics, which is the topic for today, is really important. As soon as a news item breaks in one of the wires, including social media as well, Bloomberg, the news engine, processes it in real time, tags the topics, the people, and also computes the sentiment value for each of the story. And then you can monitor those answers using Bloomberg screens. So on the left side you see all the stocks with the very highly negative sentiment, and here we have the stocks with highly positive sentiment to give investors ideas on where they should be focusing their attention on. All right, so for this talk, I'll basically first start how we extract sentiment using machine learning models from the textual data, and then there's different ways to then combine that extracted data to build sort of signals for trading. So we want to be maybe aggregate them on a company level, on different time scales, maybe at a sector level as well. And I'll show you some of the quant strategies that we build on top of these signals. And finally, some more advanced analysis on looking at specific topics in particular and specific sectors. Often we see that some clusters of topics or some styles of topics are more important for financial news than others, and it's important to highlight the ones which are more impactful. And some sectors also happen to respond in a more sensitive way to the news than others. And this is the kind of analysis that our clients they are consuming these data sets via Bloomberg feeds, and they want to get a lot of derived information from Bloomberg so that they can build their models. So the sentiment analysis framework is very typical, I would say, machine learning training exercise. So in the first step, we essentially have a lot of training data. So training data is labeled by humans, and we actually have a lot of experts in-house, because Bloomberg, being a news organization, we have industry experts, we have news journalist expertise as well, and we essentially have a large corpus of historical news stories and tweets that they have manually tagged as either being a positive, negative, or neutral sentiment. And this is from a long investor's viewpoint. So they basically look at the text, in that case, manually to train the data, and if the story would be positive to an investor with a long view on the security, or will it be negative? And they will create this database of training set. And then this training set is really what's used to calibrate the machine learning model, which I'll describe. We use support vector machines to calibrate the sentiment. And finally, then the model, when it's ready, you can run it real time as the news story comes out. So just a little bit of detail here. We operate on a story level. For each story, we have to assign a sentiment value. Then, of course, we know that sentiment is very noisy over time. Every story's sentiment could be maybe poorly captured. It may have some noise in it. So you do want to aggregate answers from many different news stories for the same company to build a less noisy indicator. So from the story level, we can create time series or company level sentiments. Those are sort of closer to what what we use as trading signals. Support vector machines are essentially, I think Tom will appreciate this. It's kind of like an optimization framework, which helps solve a classification problem. One of the, SVMs are designed for a binary classification in particular. So our problem is a little bit different because we are trying to classify every news story into one of the three classes, the positive, negative, and neutral. So we can't really use just a straight SVM. So we have to, modify the algorithm. Actually, in our case, we use an ensemble of three SVMs. So we use single SVM for each of the pairs of classification. So one for positive versus neutral, a second one for positive versus negative, and the third one for neutral versus negative. And then we combine the results into a sort of a meta machine learning model to build the final method for the three-way classification. The techniques used are very basic. At one level, we are essentially using what's known as a bag of words framework. So any document or any news story is essentially a vector in the space of the words. So if a particular word is present, a particular word from the dictionary is present in the document, then you have a 1, otherwise you have a 0. So you can think of each document as essentially a binary vector in this large dimensional dictionary space. And that makes it sort of more complex because you have very, very large dimensionality of these document spaces that you're trying to calibrate SVMs on. So SVMs are actually operating in that large high dimensional space, and the idea behind SVM is really to find the optimal plane which separates the two classes for binary classification. So we have mostly training data points in one class on one side and the other class on the other side as optimally as possible. So this will be a pictorial representation in just 2 dimensions. We obviously work with a much higher dimensional space here. So think of the red points as being stories which are labeled negative, and blue as stories which are labeled positive, for example. And we need to find this optimal line here, which separates them with some optimization criteria. So once we have that model available, we can classify any live story just by looking at the sign of this this dot product to see whether it lies on above this plane or below this plane as a classification output. Obviously, this is not a trivial problem to solve, as we appreciate there's multiple ways to build separators here, and this is where we need to frame it in terms of a mathematical problem with an objective function. In particular, what we are looking for is a plane which is maximizing the margin. So margin is essentially the distance between the closest point on either side of the yet unknown or yet undetermined line, so we want to make sure that for example, these 3 points are all equally separated away from the central dark line, and we want to maximize the distance between those points and the central line because we want to have maximum separation to have the most clean classification. So obviously this is sort of simplified because you may have training data points which could lie on the other side. The real data is usually noisy, and you don't expect to have a clean separator which will have no error rate at all. In this case, there's 0 error because all the blue points are on one side and the red points on the other side. In general, you have to allow for a margin of error, but you are still optimizing to maximize this concept of the margin. this is set up as an optimization problem. It just happens to be actually a very convex and easily solvable. Even in multiple dimension, we don't find find it to be intractable. Is essentially a quadratic optimization problem with some complementarity constraints. And yeah, so this is sort of what's behind the scene when we are solving the optimal classification problem for the binary case. So we want to go beyond just the classification, and also want to attach a confidence value to each story as well. So depending on how close the news story is to the classification line, we can judge it to be either cleanly classified or a noisy classification. So in particular, if you are near the center of the SVM line, then the classification is noisy because it's not clearly belonging in either of the two classes. If you're far away from the classification line, then you have a better confidence of your classification. And this is a simple logistic function that's used to produce a confidence number. So on the denominator, you have an exponential of the distance from the center line. So if the distance is if it's very large and positive, then you will go to 0, and if it's very large and negative, then you'll go to 1. So that's gives you a way to code for the confidence in your classification stories. So in particular, for each news story, we not only get the classification label, but we also get a confidence number, which can be used for the analytics. And this is the final classifier that we use to build the three-way classification. So as I described earlier, we use the SVM for each of the three pairwise classification. We can only do a binary classification using SVM, but here is when we combine the results from three SVMs into a larger statistical model that we build on top of it. So on each of the three axes, we have the confidence values from each of the three SVMs. So negative versus positive axis here would be the confidence value of the SVM classification, which is differentiated between negative and positive classes. As you can appreciate here, all the positive label stories have a high value on this axis, which makes sense. These are all the labeled data sets or training data sets. On this axis, we have neutral versus positive classification confidences. And again, it makes sense that for example, the negative stories will score low on this axis, but since we are not really differentiating for negative stories on that axis, they're kind of all over the place as far as this axis is concerned, but they are low on both negative versus positive as well as neutral versus negative. So you have a very intuitive picture here because it's very easy to see where each type of story belongs in this three-dimensional space. Most of the stories will line up very nicely along these corners of the cube. But we do have a small fraction of stories which are in the middle of the hypercube, or the middle of the cube here, which are more difficult to classify. And that's where we use this one of the most simple machine learning algorithms called the nearest neighbor, which essentially looks at the neighbors around the target story among the labeled points. So, for example, let's say your target story that you just are trying to classify just broke out in live news, and maybe it lands up somewhere in the middle here. You will draw a neighborhood, or sort of see a sphere, and then just capture how many of the labeled stories belong within the neighborhood, and just use the fraction of the labeled stories in each of the three classes as a way to classify for the three-way sentiment. So this is described in this simple model of nearest neighbors. So essentially, we define a distance metric, which is just a simple Euclidean distance between any two stories. And once we have a target story, we compute the distance of the target story, which is yet to be classified, against all of the labeled stories, and then we simply define, we capture the notion of the neighborhood by defining this weighting function, which is maximized at the target story or distance equal to 0, and it slowly decays with a certain bandwidth as you move away from the neighborhood. So in other words, it's not a hard neighborhood, it's a soft neighborhood. We're capturing essentially weights based on the distance from the target story. And then we simply collect the weights of all the labeled stories in each of the 3 labels, and use them as our confidence, as a 3-way confidence of the target story. If you guys have questions, we can talk later. But it's a good method to find out a confidence based classifier, which gives you not just the label. So the label will be the one which has the highest probability for the target story, but you also get a confidence number for each of the 3 labels. So any particular story could be labeled as 80% positive, but maybe 15% negative and 5% neutral. So these additional data helps us in building signals that we test for trading or predictive ability. In addition to just building that model, we also obviously place a lot of emphasis on diagnostics of these machine learning models. I guess if you're familiar with traditional data science, you probably have seen a confusion matrix. So this is a 3x3 confusion matrix for the three labels that we have, and as you expect, most of it is populated on the diagonal. So these are all our training data, and so the diagonal values are really the correct classification. So where we have the actual label matching the predicted label, and we do want to see most of these values really on the diagonal, and as few off diagonal as possible. So this is a good way to kind of dig deeper into your model and maybe help improve it, looking at properties of the confusion matrix. Another way to look at any story's sentiment is by placing it in this equilateral triangle, because essentially you have a set of 3 probabilities which sum to 1. So this will be exactly a point in this equilateral triangle, and if it happens to be exactly on the vertex, that means it's a 100% confidence on a particular label. In general, though, you will have a point anywhere in this triangle, and if you're in the center, that means you kind of have a very poor classification, or let's say noisy classification of that story. And this is how we use sort of. So this is kind of like a tool we have built internally to help with the diagnostics, to help improve the model further. So for example, here on the top left, I've highlighted the positive and positive cell there, which is one of the cells which codes for all the correctly marked positive stories. So obviously in this triangular representation, they will all end up near the positive matrix, and this is all good. But what we really want to focus on is probably the stories which are misclassified. So here we have negative stories which actually got a positive label from us, and then you can actually look at these are the tweets, and you can actually look at the text of those tweets, and probably even dig deeper into each particular tweet and see which words really impacted the score or the calculation of the sentiment. And maybe then either possibly the manual classification was wrong, or the training data itself had an error, which is a possibility, or that we didn't do the right analysis in terms of the interpretation of the words. So maybe our dictionary needs to change, or the model needs to change. So these are the kind of things we do to improve both the capture of the training data as well as improvement of the model. Okay. Once we have the results of the sentiment for every story, then we can define what we call a polarity score, which is essentially just the difference between the positive confidence and the negative confidence. So it's designed to be between -100 and +100. So it will only achieve the extreme values when it's purely classified as one of the labels. Otherwise, it will have some value in between. The neutral stories typically will come near 0, which makes sense. And this polarity score is what is used for aggregation for building trading signals. So we essentially take the polarity score of every news story, maybe in the last 24 hours, and build a simple average to build to help build an aggregate sentiment for that day, for example. We can also capture a notion of dispersion or variance on top of the average, which I'll talk about in the next slide. So this notion of variance really has two different sources. So as we saw in the calibration phase, we have possibly errors in capturing the sentiment itself. So every story may not get a pure 100% confidence in one of the labels. It may have some noisy label. So that has some variance because it's sort of like a trinomial probability distribution, essentially, which has some variance. And then the second source is obviously interstory variance, which is over time. So every single story that breaks out over the course of 24 hours will have a slightly different sentiment attached to it. So this is simply a sample variance of that changing number over time. So if we combine these two sources, we get this notion of overall dispersion, which happens to simplify to this very nice formula, which comes from the simple trinomial distribution, actually. And it's very easy to calculate because you don't need to, you only need aggregate numbers, in fact. So this is already sort of, the final formula is, it's in terms of the aggregate numbers themselves. So you don't need to really, do it story by story in a live fashion. You can just take aggregate numbers and get the variance number too. Well, this is one of the codes. So we capture the sentiment. Now we'll look at how we use it. One of the very first things we look at is just to verify the quality of the data or the signal is kind of like the correlation between sentiment and return. So this is obviously, correlation does not mean causation, and this is just to illustrate that the sentiment and markets are moving together. It's not exploitable in a trading strategy. It's not tradable. But we do notice that as we bucket the sentiment into 10 different deciles here, and we plot on the y-axis the return from the same period, same essentially 1 day period. There's a large, very significant positive trend, and the low sentiment buckets, let's say the couple of them on the left side, really have a highly significant negative return, and the high sentiment buckets have a highly significant positive return. The bars are essentially showing the mean and the standard error with essentially 95% confidence interval of that mean. So if the bars are away from the 0 line, that means that you have a significant t-stat for the return. So this gives you a good confidence that this sentiment is captured, and its markets do move together with the sentiment. But of course, what we really want to illustrate is predictability or causality from the sentiment to the return. This is a similar plot, but now the return that we are showing on the y-axis is the next day's return. So we capture sentiment over 24 hours, and then we look at the return of open to close for the next day. And you can see that the signal has weakened to a great extent, but still the last, the extreme values of the sentiment bucket still have significant results. Yeah, and the overall scale of the returns has gone down. We get about maybe 20 basis points on the extreme, or maybe even 10. But I think earlier we had about 30 to 40 basis points. Now it's like 1/3 of that, but it's still tradable. We do see that if you trade extreme sentiment values, there's a potential to be profitable. So we employ a very simple trading strategy. Again, we didn't want to over optimize the construction of the trading strategy itself. We wanted to keep it simple. There's a potentially we want to create strategies which are robust and not prone to data snooping. So we essentially want to create something very simple, easy to replicate. A candidate is simply a traditional quintile long short strategy, where we just after bucketing the sentiment into maybe 10 buckets, we essentially look at the extreme values on the positive and the negative side, and we go long the stocks with a highly positive sentiment, and we go short the stocks with a highly negative sentiment. And we just try a couple of flavors here with the top 1/3 and bottom 1/3, and top 5% and bottom 5%, to see the difference. And then the third flavor really is not a binary weight on the stocks, but a weight proportional to the sentiment itself. So it's actually taking positions in all the stocks, but in proportion to the sentiment, as subtracted from and once you subtract the cross-sectional mean out. So this is just the formula for that. We don't have to look at this detail, but this is the result of that long short strategy. So on the x-axis we have the 4 different strategies. The rightmost one is just the index itself. In this case, it will be the Russell 2000 index. So these are this is all the 2000 stocks of Russell 2000. And as you can see, the return of the index, the standard error around that is crossing the zero line. So that means the t-stat is not significant. So we really can't confidently say that index itself had a significant return over that period. But each of these 3 strategies had a significant positive return. We had lower mean for the 1/3 strategy. We had a higher mean for the 5%, and proportional was in between. In the Sharpe ratio sense, they are actually all similar, because you can see that the one with the 5%, the yellow bands are much wider. That's because we take position in very few stocks. We're only focusing on top 5% and bottom 5%. So we don't get the benefit of diversification, and the volatility of that strategy is higher. So once you convert that, the mean and the standard deviation into a Sharpe ratio number, they are all comparable and pretty good. This is an illustration of the P&L. There's a caveat here that we didn't, in this case, we didn't take into account the trading costs, which actually happens to be a very big factor for these types of strategies, since we are rolling daily. And I'll show you the effect of that. A lot of your predictive signal will get wiped out. Some survives, but here what we are showing is without the transaction costs, and with the inclusion of the dispersion metric as well. So we include the stocks with high sentiment and low dispersion. So we create this long and short portfolio with a more nuanced rule. And you can see that the ones with the dispersion, in addition to the sentiment, perform even better than just the sentiment alone. These are the numbers without transaction costs. Again, these charts are, they're actually not realizable. So they look too good for a reason, but it basically shows you the power or the availability of information in these sentiment signals. In terms of converting that into a profitable trading strategy is, we need to do that with some more care. There's one more slide here which shows that if you combine the signals from two different sources, news and Twitter, there's some decorrelation between those signals. So once you combine them, you are able to actually extract a higher Sharpe ratio. So you get much better looking P&L curve. And essentially, you are reducing the volatility of your portfolio by doing this diversification across two sort of independent sources of information. So this actually shows you the illustration with the transaction cost. As you can see, some of the strategies did not perform well, and these are very high turnover strategies because we are building a new portfolio every single day, and a lot of that, a lot of the stocks that you long yesterday are maybe going to be not in the picture tomorrow, or may actually you might have to go short them the next day. So there's some work to be done to maybe optimize for trading cost concerns, but still, even with trading costs, we see that some of the strategies do show a good performance, especially when you combine with dispersion. And we have tested these for about 10 years of data, and we see that these strategies perform even during the crisis actually pretty well. So you can see actually broken it down by the long side only as well as the short side only. So the blue line is the overall strategy, but you see the red is only the short side of the portfolio, and the green is the long side. So especially during the financial crisis, the short side actually performed very well. But in general, they both have performed over time, resulting in this great performance for the blue line. And we also look at the same signals in variety of different contexts. You don't have to just build a factor strategy, but you can also look at certain strategy around specific events like earnings, for example. There's reason to believe around earnings. The surprise in the earnings carries a lot of weight on what the post earnings drifts might be for the stocks. So we take a position in stocks which have which have positive sentiment just before the earning release, and we see that helps in actually getting a very good P&L. And the caveat here is that there's fewer events, so you may have more volatility in these numbers. In general, you have better return available, but maybe with some more volatility. So in terms of Sharpe ratio, it may not be as good. But this strategy actually works not just for the Russell 2000, which were small caps, but also for the S&P 500, which are the largest stocks in the U.S. So the simple strategy I described earlier with the long short method was not significant for large caps, and the reason might be that the information in the news is probably already absorbed in the markets for the large caps, and news is sometimes reactive to the events, so it gets made available sort of as a reaction to the event rather than something that investors don't know about. But in small caps, there is a reason to believe that news is actually a leading indicator. So the sentiment attached to the news is possibly helps you get an advanced signal for the trading. All right. So, and we also looked at how the news gets, or the signal in the news gets absorbed on an intraday basis as well. Some of our clients are interested in high frequency trading, and they look at the signal in the news story as it breaks out over a matter of minutes. So we're looking at 20 minutes after the news story, and you look at how the expected return or the mean return and the standard error bars changes as a function of this lag. And you can see that there's a sustained increase in the beginning, and then it sort of flattens down, and that's possibly an indicator that for a single news story, maybe you should try to trade it within the 10 minutes. If there's any signal available, it's probably gets wiped out after 10 minutes. Okay. So these are sort of the basic strategies. We also have more nuanced or enhanced versions of creating more complex portfolio strategies using sentiment. So in particular, most of us are familiar with the Markowitz mean variance framework, and so think of the sentiment signal as essentially a signal for expected return for the stocks. So you have your typical covariance matrix estimated from historical returns of your underlying stocks, but you replace the expected return by the sentiment value, and see that should essentially help you not just take positions in stocks with high sentiments, but also control for correlation. So if there's high correlation between two stocks with high sentiment, it will not overweigh those stocks because it will also try to take a diversified position. So if you do that, you can further increase the value in these signals. So you look at the blue line is the I think it's the older method. I'm sorry, the yellow line is the older method. The blue line is the enhanced with the mean variance optimization. And you can see they generate the same return, but the blue line is much smoother. So the volatility of the blue line, if you can see the table here, is essentially actually half of the yellow line. So we have 6% vol versus 3% vol, which leads to almost doubling of the Sharpe ratio. Yeah.
Does that picture include transaction costs or
no, this one doesn't. Yeah, transaction costs are obviously very important in this case. And how much time do we have? Yeah, well, this is another set of nuanced analysis to make even the standard sentiment signal work on large caps by combining with other signals. So we saw that the sentiment signal was really valuable for small caps, but not for large caps earlier. But we know that in S&P, there's a lot of people believe in momentum strategies. So there's a certain mean reversion that comes into play at short horizons, even for large caps. And turns out if we combine the signal from sentiment with this momentum / mean reversion signal, we can actually extract value even for large caps. So essentially, we build portfolios which are long short in sentiment, but also filtered by their momentum signal to combine the two into one composite signal and achieve performance that are better than just either of them applied on their own. One more item I wanted to address in the last part of this talk was the analysis of the topic codes. So as I discussed earlier, every news story gets the sentiment score, but also gets tagged with all the relevant topics that are present in the story. So for example, a story could be about sports, so it gets some sports topics, or it could be about company default or analyst news. So all of those topics, we have a big taxonomy of these topic codes, literally hundreds and thousands of them, and they get tagged automatically by our machine learning algorithms as well. In this study, we want to find out which topic codes are more relevant for trading purposes. So essentially, we are able to essentially distill the topic codes into different clusters of the codes. So here's one cluster, which is what we have named controversial topics. So these are topic codes to do with, litigation or IP lawsuits, and so on. And turns out this cluster of codes was actually very less predictive in actually company performance. This is because the language in those stories about the companies which are going through these kind of events is much more about the event itself rather than the impact on the company performance. It turns out when we remove those top 10 controversial codes, we actually get a better signal. So we get better correlation of the return versus the sentiment. So we can actually improve our sentiment capture by paying attention to what topics are being addressed in every story. On the flip side, we also have a different cluster, which are to do with key company news around analyst activity in particular. So these are the topic codes that Bloomberg has, and these are essentially your analysts which are covering those companies are writing about a company's performance, and these happen to be very impactful in driving the returns of the securities. So and these are the different cuts we have done to show that if you were to include the good topic codes and remove the bad topic codes, then you get increased performance. And these are sort of the different combinations of including and not including those codes. But clearly we see that the topmost one is we include the good topic codes and we remove the bad topic codes, and we get a much higher performance of the returns. And just to wrap up, we have done studies to show that earlier I talked about how sentiment is sensitive to the small stocks. So this shows you that if you look at the market cap, only the bottom 1/3 of the companies in terms of market cap, then we have a higher slope of the sentiment versus return. And for the large caps, we have a very small sensitivity. But if we further color it by also volume, we see that it's the high volume which has slightly better sensitivity for sentiment. And then in this picture, we combine the two into a sort of a two-dimensional bucketing. So we look at different buckets of small cap and small volume, and small cap and large volume, and so on. And clearly we see that we get the best results in this lower left quadrant here, which are essentially small companies but with large trading volumes. So this is where investors can probably draw more value. And there's some other analysis we've done for sectors. We find that certain sectors have more sensitivity to sentiment captured. For example, consumer cyclical ones and technology. I think we note that there's a lot of activity around that in social media, those kind of companies. So perhaps that makes sense. Yeah. So with that, I end my talk. Thank you very much.